Dione is a moon of Saturn. It was discovered by Italian astronomer Giovanni Domenico Cassini in 1684. It is named after the Titaness Dione of Greek mythology. It is also designated Saturn IV. Giovanni Domenico Cassini named the four moons he discovered Tethys, Dione, Rhea and Iapetus Psider Laodoisa, the stars of Louis, to honor King Louis XIV. Cassini found Dione in 1684 using a large aerial telescope he set up on the grounds of the Paris Observatory. The satellites of Saturn were not named until 1847, when William Herschel's son John Herschel published results of astronomical observations made at the Cape of Good Hope, suggesting that the names of the Titans, sisters and brothers of Cronus be used. Dione orbits Saturn with a semi-major axis about 2% less than that of the Moon. However, reflecting Saturn's greater mass 95 times that of Earth, Dione's orbital period is 10% that of the Moon. Dione is currently in a 1:2 mean motion orbital resonance with Moon Enceladus, completing one orbit of Saturn for every 2 orbits completed by Enceladus. This resonance maintains Enceladus' orbital eccentricity, 0.0047, providing a source of heat for Enceladus' extensive geological activity, which shows up most dramatically in its cryovolcanic geyser-like jets. The resonance also maintains a smaller eccentricity in Dione's orbit, 0.0022, tidally heating it as well. Dione has 2 co-orbital, or Trojan, moons, Helena and Polydeuces. They are located within Dione's Lagrangian points L4 and L5, 60 degrees ahead of and behind Dione respectively. A leading co-orbital moon 12 degrees ahead of Helena was reported by Stephen P. Sinnott in 1982. At 697 miles in diameter, Dione is the 15th largest moon in the solar system, and is more massive than all known moons smaller than itself combined. It is also Saturn's 4th largest moon. Based on its density, Dione's interior is likely a combination of silicate rock and water ice in nearly equal parts by mass. Shape and gravity observations collected by Cassini suggest a roughly 248.5 miles radius rocky core surrounded by a roughly 99.5 miles envelope of H2O, mainly in the form of water ice, but with some models suggesting that the lowermost part of this layer could be in the form of an internal liquid saltwater ocean, a situation similar to that of its orbital resonance partner, Enceladus. Downward bending of the surface associated with the 0.9 miles high ridge Janiculum dorsa can most easily be explained by the presence of such an ocean. Neither moon has a shape close to hydrostatic equilibrium, the deviations are maintained by isostasy. Dione's ice shell is thought to vary in thickness by less than 5%, with the thinnest areas at the poles, where tidal heating of the crust is greatest. Though somewhat smaller and denser, Dione is otherwise very similar to Rhea. Both have similar albedo features in varied terrain, and both have dissimilar leading and trailing hemispheres. Dione's leading hemisphere is heavily cratered and is uniformly bright. Its trailing hemisphere, however, contains an unusual and distinctive surface feature: a network of bright ice cliffs. Scientists recognize Dionian geological features of the following types. 1. Chasmata chasms, long, deep, steep-sided depressions or canyons. 2. Dorsa ridges. 3. Fossae, long narrow depressions. 4. Craters. 5. Catenate crater chains. 6. Ice cliffs, formerly wispy terrain. When the Voyager space probe photographed Dione in 1980, it showed what appeared to be wispy features covering its trailing hemisphere. The origin of these features was mysterious, because all that was known was that the material has a high albedo and is thin enough that it does not obscure the surface features underneath. One hypothesis was that shortly after its formation Dione was geologically active, and some process such as cryovolcanism resurfaced much of its surface, with the streaks forming from eruptions along cracks in the Dionian surface that fell back as snow or ash. Later, after the internal activity and resurfacing ceased, cratering continued primarily on the leading hemisphere and wiped out the streak patterns there. This hypothesis was proven wrong by the Cassini probe flyby of December 13, 2004, which produced close-up images. These revealed that the wisps were, in fact, not ice deposits at all, but rather bright ice cliffs created by tectonic fractures chasmata. Dione has been revealed as a world riven by enormous fractures on its trailing hemisphere. The Cassini orbiter performed a closer flyby of Dione at 310 miles on October 11, 2005, and captured oblique images of the cliffs, showing that some of them are a couple thousand feet long. Dione features linear vergi that are up to hundreds of km long but less than 5 kilometers wide. These lines run parallel to the equator and are only apparent at lower latitudes, at less than 45 degrees north or south. Similar features are noted on Rhea. They are brighter than everything around them and appear to overlay other features such as ridges and craters, indicating they are relatively young. It has been proposed that these lines are of exogenic origin, as the result of the emplacement of material across the surface by low-velocity impacts of material sourced from Saturn's rings, co-orbital moons, or closely approaching comets. Dione's icy surface includes heavily cratered terrain, moderately cratered plains, lightly cratered plains, and areas of tectonic fractures. The heavily cratered terrain has numerous craters greater than 62 miles in diameter. Plains areas tend to have craters less than 19 miles in diameter. Some of the plains are more heavily cratered than others. Much of the heavily cratered terrain is located on the trailing hemisphere, with the less cratered plains areas present on the leading hemisphere. This is the opposite of what some scientists expected. Shoemaker and Wolf proposed a cratering model for a tidally locked satellite with the highest cratering rates on the leading hemisphere and the lowest on the trailing hemisphere. This suggests that during the period of heavy bombardment, Dione was tidally locked to Saturn in the opposite orientation. Because Dione is relatively small, an impact causing a 22 miles crater could have spun the satellite. Because there are many craters larger than 22 miles, Dione could have been repeatedly spun during its early heavy bombardment. The pattern of cratering since then and the bright albedo of the leading side suggests that Dione has remained in its current orientation for several billion years. Like Callisto, Dione's craters lack the high relief features seen on the Moon and Mercury. This is probably due to slumping of the weak icy crust over geologic time. On April 7, 2010, instruments on board the unmanned Cassini probe, which flew by Dione, detected a thin layer of molecular oxygen ions O+2 around Dione, so thin that scientists prefer to call it an exosphere rather than a tenuous atmosphere. The density of molecular oxygen ions determined from the Cassini plasma spectrometer data ranges from 0.01 to 0.09 per centimeter cubed. The Cassini probe instruments were unable to directly detect water from the exosphere due to high background levels, but it seems that highly charged particles from the planet's powerful radiation belts could split the water in the ice into hydrogen and oxygen. Dione was first imaged by the Voyager space probes. It has also been probed 5 times from close distances by the Cassini orbiter. There was a close targeted flyby, at a distance of 310 miles on the 11th of October 2005. Another flyby was performed on the 7th of April 2010 also at a distance of 310 miles. A third flyby was performed on the 12th of December 2011 at a distance of 62 miles. The following flyby was on the 16th of June 2015 at a distance of 321 miles, and the last Cassini flyby was performed on the 17th of August 2015 at a distance of 295 miles. In May 2013, it was announced that NASA's spacecraft Cassini had provided scientists with evidence that Dione is more active than previously realized. Using topographic data, NASA teams deduced that crustal depression associated with a prominent mountain ridge on the leading hemisphere is best explained if there was a global subsurface liquid ocean like that of Enceladus. The ridge Geniculum dorsa has a height of 0.6 to 1.2 miles. Dione's crust seems to pucker 0.3 miles under it, suggesting that the icy crust was warm when the ridge formed, probably due to the presence of a subsurface liquid ocean, which increases tidal flexing.